Okay. All right, so the new topics we're covering is in chapter 9 and 10, and just one little section of 11 where we skipped the last ellipsis. I'm going to go in a slightly different order than in your textbook because I think we can cover the material a little bit easier that way. Okay, so don't worry, we're going to go a bit faster, but in a slightly different order, but we're going to cover everything. Okay? So we're going to talk about the work done by, we're going to talk about work. Okay. So let's talk about the work. Let's maybe zoom in a little bit more. Oops, that was not good. What's going on with this? Okay, when I lock it, it goes.
You could say it doesn't work.
It doesn't work. Okay, let's see. It's focusing on the wrong thing. Okay, now there it goes. Okay. Okay, so the work done by a constant force. So something that's not changing with time. Okay? Maybe that's why I wasn't doing the right thing. It was not straight. So for constant forces, by constant forces I mean, let's say, I have these weights here, heavier than I thought. And I press against the side here with a constant force. It feels the same every time along, and I push it. Okay, I want to know how much work I'm doing. So in physics, this has a very definite meaning. So let's just draw the figure here. Okay, and let's say I have, this is a force, and it's a constant force, F.
You're writing off.
Yeah, thank you. There we go. Let me move this up a little bit so I have more space. And now let's say the actual object moves this displacement d. Okay, this is d, that's the displacement. And let's say there's an angle between the force and the displacement. Then I'll first write it in words. For constant forces, the work done is the product of the magnitude of displacement, how big you displace it, how much you displace it, big is not really the proper word, and the component of force in the direction of displacement. Okay, so if you don't like this in sentences, if that's a bit confusing, let me just show you in equations. So we have this force here, F. Then we would say the work done by force F is, and that's capital W for work, and it's F times D times cosine of the angle between them. Okay, so if you can't see that figure up above, well, let me just draw it again. D is the displacement, theta is the angle between them. Okay, F times D times the cosine of the angle between them. angle between F and D. So without the vector hat, F is the magnitude of F. Without the vector hat, D is the magnitude of D. So, yeah.
So is work a scalar?
Work, that's a great question. So let me ask you, is work a scalar or is it a vector? Yeah, it's a scalar. It's a scalar. It's just a number. It can be positive or negative, but it's just a number. Okay, so where did I get this formula from? Well, the way you can think of it is, well, let's just do it carefully. So if I have F here and F of D here, okay, what I'm going to do is take the product of the component of F in the direction of the displacement. So this is the direction of the displacement. So I need this component here, but this is the angle theta, and this side is the adjacent side to theta. So that's why this is going to be F cosine of theta. And then if I multiply this and this, that is going to give me the formula FD cosine of theta. Okay. Pretty good. Okay, now let's talk about when the work is positive and when the work is negative. So if the force component, the piece of the force in the direction of the displacement, if the force component is in the same direction as displacement, the work is positive. Okay, the example I've been drawing is exactly that case. We have force here, we have displacement d like this, okay, and the component is this guy over here, and it's pointing in the same direction as d. Okay, it's not going the opposite direction, it's going the same direction. I'm talking about this component here, okay, this component here. And so in this case, F does positive work. And in fact, we have a formula for how much positive work it does. It's F times D times the cosine of theta. And if you don't believe me, you can check that it's positive by just putting in numbers, right? If I put in numbers for theta, let's say 0 degrees, what is the cosine of 0? Yeah, 1. So in the special case where theta is equal to 0, or in other words, F points in the same direction as D, then it's just F times D. And this is the more basic formula. When the force and the displacement point in exactly the same direction, it's just simply F times D, and it's positive. Now, if the force component is opposite to displacement, then the work done is negative. Okay, so let me give you an example. You might be a little confused by this, but I'll explain in just 1 second. Let's suppose the force goes like this, but the displacement is in this direction. And you might, the thing that might be confusing to you is how the heck can you pull in this direction and the thing move in that direction, right? That's kind of weird. Okay, sure, thank you. Very good. Okay, so what's going on here is there's other forces. Somebody else is pulling in the other direction, and they're pulling a little bit maybe harder, just slightly harder, so it's moving in that direction. Okay? So in this case, we have then this component that's pointing in the opposite direction to D. Everybody's agreeing with me on that? Okay. And so in this case, F does negative work. Okay. So you can check that as well. So I said theta is the angle between f and d, the vectors f and d. So if you do w is equal to f times d times the cosine of theta, and try, for example, theta equals to 180 degrees. Anybody know what that would be cosine of 180 degrees?
Negative.
Yeah, negative 1. So that would be when d is this way, f is that way, then you have f times d times the cosine of 180 degrees, or which is equal to -1. Okay. Any questions about this? Yeah. Yeah, I'll get to the concept. I'll try to. Yeah, so I'll make now the connection what exactly work is. First give you the definition. So I'll try to make the connection. Okay. So the units for work is actually, the SI unit is 1 joule, 1 J joule. Okay. And 1 joule is 1 Newton times meter. So from the formula, you can sort of figure that out. Force is newtons, has units of newtons. Distance or displacement has units of meters. So newtons times meters. If you wanted to pull out all the more fundamental units out of this, then remember Newton. Does anybody remember Newton's, what it was in terms of kilograms, meters, and seconds?
Kilogram meters per second.
Yeah, you guys have that. So this was kilograms, meters per second, kilograms, meters per second squared. This ends up being 1 kilogram meter squared per second squared. Okay? So this is the same, actually has the same units as something we're going to talk about a little bit later. It has the same units, so work has the same units as something we haven't talked about yet, but energy. So work is actually related to the transfer of energy through forces, okay? Work is the transfer of energy due to a force and displacement. Okay. Specific kind of transfer of energy. There's other kinds of transfers of energy. Any questions about this? Everybody's good on that? Okay, so let me give you a mental picture of that I think helps. So maybe there's a lot of it. Yeah, there. Don't worry, it's nothing embarrassing. It's just kind of, and we're going to pretend we're pushing each other. Okay. So you're going to push me. So you're just going to push me, and you just keep pushing. So who's doing positive work? He is, because he's pushing this way, okay, and we're moving that way, okay. But how about me? Am I doing positive or negative work? Negative work. Okay. Thank you very much. Okay. So yeah, have that mental image. Okay, there's a pushing match going on. If you get your way, you either push and it moves in that direction, or you pull and it moves in that direction. You do positive work. Whereas the person or whatever is losing will be doing negative work. So that may sound kind of funny. How can somebody be doing negative work? Well, you can think of it, doing negative work is sort of like storing up energy. You could, for example, we'll talk about springs in a moment. You could have like a little spring, and because the spring is losing, it's actually starting to store some of that energy so that then you can take it and do something else later. Okay. Does that make sense? Okay, another example is this. You have this weight. Gravity is pushing down. I'm pushing up. Right now, it's not moving. But now suppose, well, I don't have to suppose I'm going to do it. I'm going to lift it up. Okay, am I doing positive or negative work? Positive, because I'm pushing and I'm winning. Okay, the negative is, the gravity is doing negative work as I push it up. But it's actually storing it in something that we'll talk about called potential energy, because now it's gotten to this point here, it can do something with that energy, in particular when I let go, it's going to start falling. Okay? So that's the idea of negative energy. It's being stored in some other form. Okay, let's now talk about something with vectors that we need to be able to define work in a little simpler way. So we're going to talk about the dot product or the scalar product. And let me ask, how many of you have seen the dot product or the scalar product before? Okay, so maybe about half of you. So for those of you who haven't seen this, I'll try to make it very clear. So this is what's called the scalar, or very often it's called the dot product of two vectors. Okay, so in order to define it, you need two vectors, you dot them together, you make a scalar product of the two. And so let's say A and B are vectors. And let's say A is kind of like this, and B is maybe like this, and there's some angle between them, let's call it theta. Then the scalar, or the dot product, is written as this. And you'll see why it's called dot product, because we put a big fat dot between them, okay? This is the symbol A dot B is equal to A times B. So remember, when I just write plain old A or plain old B, that means the magnitude of A, that means the magnitude of B. That's what's meant by these things without the vector hat, times the cosine of the angle between them. So we say this is the dot product or scalar product. All right, and it's not a vector. That's why it's called scalar product. It's just a number. So now with this, we'll do more with the dot product later. We'll do things with complements later, but this is enough for what we need for now. So with this definition of the dot product, so now we can write work W, this formula we just defined for a constant force, is W is equal to the vector F dotted with the vector D. Okay, so I claim that's the same thing I said before, and we can just check it. We're going to now just plug in the definition of the dot product here. It will be the magnitude of F, which is just plain old F, times the magnitude of D, which is just plain old D, times the cosine of the angle between them. And we can look back, and we'll see that that was exactly the same formula we had before. Okay, that's what we had before, FD cosine theta. All right? Any questions about this? So we can just write F dot D as vectors. Now let's play around a little bit more with dot products. So if, let's go back to saying A and B. If A and B, the vectors, are perpendicular, then when I do A dot B, so perpendicular means like this, so they make right angles to each other. So A dot B will be A times B times the cosine of the angle between them, but the angle between them will be 90 degrees, and the cosine of 90 degrees is equal to what? 0. Okay, that's equal to 0, and so the dot product will be equal to 0. So if I take a dot product of two vectors that are perpendicular to each other, then I'll get 0. Similarly, if this is a very simple example, I'm going to push this weight. I'm going to do positive work. Okay. By the way, let's talk about friction as well. So I'm winning against kinetic friction. Kinetic friction is opposing me, but I'm winning. Okay. By the way, friction pretty much never wins. It just resists the motion. So it's always going against the motion. So if the displacement is this way, then the friction is going off the ground. Okay. All right, so I'm doing positive work. Friction is doing negative work. Gravity. How about gravity? What kind of work is it doing? Is it doing any work at all? No. That's because the displacement is horizontal. The gravity, of course, is going vertically. And so when I do F dot D, I'll get cosine of 90 degrees, which is 0. Okay. Does that make sense to everybody? Okay. That's this case here. When A and B are perpendicular, the dot product is equal to 0. Okay. Any questions this far? Now we're going to explore a little bit more about energy. And the type of energy we're going to discuss is kinetic energy, which is the, well, let me finish writing this in a second. I'm going to tell you. So one type of energy is kinetic energy. So we write, the symbol for kinetic energy is capital K. So I like to say that kinetic energy is the energy stored in some sort of, well, I don't know if I really need quotes, but it's a conceptual thing. Stored in a moving object. Okay. And it comes with a very simple formula. So kinetic energy, there's one formula that goes with it for an object with mass m and speed v. Remember, speed is the magnitude of the velocity. The kinetic energy is capital K is equal to 1/2 times m times v squared. Okay. All right, and as I said, energy has units. So kinetic energy is a specific kind of energy, so it has units of 1 joule, where 1 joule is equal to 1 Newton meters, and we said that can also be considered as 1 kilogram meters squared per second squared. Okay. Questions about this? All right. So one way to think about energy, if I were to throw this, there'd be some energy stored in the fact that it's moving with its mass. Okay. The more mass it has, if I threw this with the same speed, it'll have more energy. If I threw it harder, it will have more energy. Okay. So let's just give you a very simple calculation. So a 1 kilogram mass with speed 1 meters per second has kinetic energy. It's very simple. K is equal to 1/2 mv squared. So then we will have 1/2 times 1 kilogram, 1 meters per second squared. And so we end up with 1/2 of a joule. Okay, just converting kilogram meters squared per second squared to joule. Yeah. Yeah, that's a good question. Why is it 1/2? One way to think about it the, there are actually a lot of formulas like this. In fact, if you look towards the end of the lecture notes, which I don't think I'll get to today, there's another formula where there's a 1/2 kx squared that will be coming up. But it comes about from doing integrals. If you were to figure out how much energy is stored in something, if you're doing an the 1/2 is the same 1/2 you get as if I were to do an integral of x dx. What is integral of x dx? I get a 1/2 x squared. It comes from this type of a formula. Okay, so I'm not deriving this formula here, but that's kind of how it comes about. A lot of formulas where something is squared comes with a 1/2 just because it comes from some formula like this. Good question. All right, let's go on. So any questions, other questions? By the way, while we're staring at this formula for kinetic energy, some of you might know or have heard of relativity. How many of you heard of relativity? Okay, so the special theory of relativity that Albert Einstein wrote down in the miracle year of 1905. He said that there was more energy than just kinetic energy in a mass, some massive object. And the formula for that, you can almost guess it just from the units of this. And there was a formula that the rest energy, the amount of energy in an object with a mass m, and his formula was that the energy is mc squared, where instead of having the speed of the object, c is the speed of light. So if you take the speed of light, which is 3 times 10 to the 8th meters per second, and you plug that in mc squared, that's the rest. That's the energy you could get if you took all these atoms and stuff and you just smashed them together and then just released all the energy out. And it's a tremendous amount of energy. So, any questions about that? Okay. Now, the next thing we'll talk about is something that has a name. It's called the work energy principle. Okay. So, let me tell you what is the work energy principle. So we're going to connect these together. Okay, the statement of the work energy principle is, and I'm going to say the word network, not network like internet network, but the network done. Network done by all forces on an object is equal to its change in kinetic energy. Okay. All right, so your book uses the symbol W sub ext for external, but I find it easier to just write net, W sub net. And that's the total work done by all forces. Okay? You say, how much work did force 1 do? How much work did force 2 do? How much work did force 3 do? And you add them all together. Because they're not vectors, the work is not a vector, it's just a number, it's just a scalar. You can just add them together. You could actually, however, decide to add the forces together as vectors and then figure out the net force and then ask how much work does the net force do. And it gives the same answer. So this is also equal to, so you can think of it as the total work done by all the forces added together, or it's equal to the work done, not the word done, work done by the net force. And they're the same. Either one. Okay? So just the net work. And the formula is that it's equal to the change in the kinetic energy. So this delta means the change. So we have the change in kinetic energy. All right. Any questions about this? So what it's saying is, suppose I, with my hand, I'm accelerating this pen. Okay, I'm throwing it. So I'm going to be doing work as I go from here to there. And the work that I have done on this pen, moving it horizontally, by the way, gravity isn't going to be, well, let's say we're in outer space, so gravity's not there. Okay? And I'm just throwing the pen. Then I'm going to do some work, and the amount of work I do will be the amount of kinetic energy this pen has after the release from that pen. Okay? Now, this would also work on Earth where there's more forces acting, but then you have to calculate the work done by all the forces. Okay? So let me give you an example now. Okay. Let's say a 10.0 Newton force pushes on a 2.0 kilogram mass over a horizontal distance. Of 10 meters. Okay, so if the surface is frictionless, and the box starts from rest, how fast is the, okay, sorry, I forgot. So I called it a mass and it became a box. So it's a mass and a box at the same time. Okay. So how fast is the box moving at the end? Okay, let's just say box. All right. Now, question, yeah.
The force in the same direction.
Yeah, I was going to draw a picture. Sorry, I meant to draw a picture. Ran out of space. That's actually a perfect question. Without knowing that, you couldn't really solve the problem. Okay, so let's go on this side. So here's the picture that goes with that. We have, oh, that's supposed to be straight. I didn't draw it very well. 10 newtons. We have the box like this, okay, and it's 2 kilograms. And we want to know how fast it's going at the end. All right, so we actually can solve this problem using quiz 3 material. We could say, what is the acceleration on the box, right? We know there's 10 newtons. We know it's 2 kilograms. Acceleration is, right, F equals ma, acceleration equals 5. And then we'd say it moves a distance of 10 meters. We know the acceleration is 5, starts from rest. How fast is it going? It smells a lot like problem number, whatever, 5 or something on your quiz 3, right? Remember that? It was at an angle slightly? Yeah, bad memories of that problem. Yeah. Okay, so we could solve this using Newton's second law, but we can solve it faster using this work energy principle. So let's use the work energy principle. So let's find out the work done by the net force. Okay, so let's first figure out what is the net force. Well, there's only one force that really matters here. The vertical forces are going to cancel out here. So it'll be F dotted with F net dotted with the displacement vector, d. Okay, so what is the angle between the displacement and the force? What is it? Yeah, 0. So we'll just have F net times d times cosine of 0, and that's just equal to 1. So just the product of the two. So this will be, so it's not that hard. It's going to be 10 newtons times 10 meters. And so we get 100 joules. So we figure out that delta K, change in the kinetic energy, is 100 joules. And since the initial kinetic energy, what is the initial kinetic energy going to be? Yeah. Why is initial kinetic energy 0? Yeah, it starts at rest. So the initial kinetic energy is equal to 0. So then that means that the K final is just going to be the change in the kinetic energy. And so that will be equal to 100 joules. We're almost done. So that is going to be also equal to 1/2 the mass times V final squared. Okay. So we have 1/2 mv final squared is 100 joules. This thing was 10. So I can times 2 and divide by 10. And then I end up with, so mass is 2. Yeah, mass is 2. Yeah, that's right, because my numbers weren't working in my head. Okay, sorry about that. I lied. The mass is 2. So then 1/2 cancels the 2. And so V final is equal to 10 meters per second. Okay? Any questions about that? All right, now the time remaining, let's do one clicker question. Okay. Let's say let me just draw the figure. Another box on the floor. Let's say it's 4 meters is the displacement. And then we have a force like this, F, and this angle is 37 degrees. And let's say F is 55 newtons. And the question, and this is a horizontal floor, and this mass M, this mass here is 16 kilograms. The question is, what is the work done by force F? Okay, A, B, 76 joules, 132 joules, C, D, E, we have 220 joules, we have 627 joules, oops, and then we have 0 joules. Okay, and I'll open up the poem now. By the way, I'm selecting my quicker questions from all the practice problems, the bank of problems I have, so I'm selecting the quiz 4 problems. Okay, I'll give you another 30 seconds. Okay. If you haven't made a choice, go ahead and make a choice. All right. Okay. Let's see what people said. Oh, a lot of people said A. Very good. So, work is F times D times cosine of the angle between the two. So F is 55 newtons, D is 4 meters. We have the cosine of 37 degrees. Put this into your calculator and you get 176 joules. Okay. All right, I'll see you guys tomorrow.